project for Digital Museums Canada. It's a project that was based on the thesis of Dan Posey here in Victoria, and it looks at the early years of the observatory and its impact on science, national, civic identity, and tourism. Early on, this was a big tourist attraction. People would come from around the world to see it. It had an impact on the city, on national identity. The early years is really a fascinating story. So this website will take you there. It goes backwards. Okay. And then the second one is released this year is a documentary called Northern Star. It's based on the biography of John Stanley Plaskett that was written by Peter Broughton. So this was shown on Czech TV, so that website that will take you to the Czech TV website where you can stream it. And we have a birthday today. No, anybody's birthday in the audience by chance? No, I didn't think so. Harry Henley Plaskett, John Stanley Plaskett's son, was born on this day in 1893. He ended up being an astronomer as well, and a very accomplished astronomer. He worked here for a bit, went to Harvard, and then after Harvard, he became the civilian professor of astronomy at University of Oxford, where he worked until he retired. So, like I say, a very accomplished astronomer on his own right. So, must run in the family. There's his picture. So, I need to find out where I can. I'm going to block people's view no matter where I stand. Okay, I'll just stand here. So, tonight we're talking about capturing the cosmos with the Rubin Observatory's Legacy Survey of Space and Time. That used to be the name of the telescope, but then they named the telescope after Vera Rubin, and they wanted to keep the acronym, so they came up with that for the Legacy Survey of Space and Time. And they really do mean not only space, but how the universe changes over a 10-year period. What things change if you look at it. And so ultra-wide, ultra-high definition time-lapse record of the observatory. And in a sense, you can think of it as a movie. So here's a little bit about Vera Rubin. She was a very accomplished researcher, a trailblazer. She provided the first concrete evidence for dark matter, which is a big constituent of baryon matter in the universe that we have no idea what it is. One of the big mysteries of the universe. And she also was a very strong advocate for women in astronomy. So the Vera Rubin Observatory is the first major U.S. observatory named for a woman. And there are the names they would like you to use. So there you are. And she even has a quarter with her on it now in the U.S. So quite the thing that the U.S. has put her on a quarter. I met Vera Rubin when I was a grad student in Toronto, and she was doing her work on rotation curves of galaxies. So up until, the 1970s or so, early 70s, people thought that what we saw in a galaxy, the starlight was all there was. And starlight's concentrated to the center. And so like our solar system, where the sun is most of the mass in the solar system, the rotation velocity of things as you go further out will go down as you get further away from the mass. But her work, when she looked at rotation curves of galaxies, the rotation curve flattened out. It didn't go down like everybody thought it should. And she had a hard time convincing people this was real, but that only way you could explain that was by some unseen dark matter that was much bigger than what you saw, the visible light in the galaxy, and that's what kept the outer parts of the galaxy rotating at higher speeds. So, where is the Rubin Observatory located? It's in Chile. There we go, take out my laser pointer. Down in Chile here, where it's winter right now. It's located just outside La Serena in Chile, where I lived. A nice little spot by the ocean. And inland from there are a couple of observatories, hill mountains or whatever, that have observatories on them. Cerro Tololo was built in the 1960s, and then Cheryl-Pichon was developed in the late 1990s. And there we have a picture of the Rubin telescope and building. It's a very unique observatory building style. And flip back to this. So here's another look at it. There's another nice picture of Rubin. And here we see the telescope, the support building under construction. Here we have an auxiliary telescope. It's used for calibration of data and images. And off in the distance, you see Gemini South. So Gemini is twin telescopes, one in Hawaii, one in Chile. That's who I worked for when I lived in Chile. CAD is a partner in that telescope. And then over there we have SOAR. So the mountains are in the foothills of the Andes at about 2,700 meters elevation. So what is the mission of the Rubin telescope? Wide field of view. So it's like your camera or your phone, if you got different lenses on your phone. You can have the normal camera or you can have a wide field look. Field of view captures more of what you're looking at. The sky is a big place, and so Rubin, with a wide field of view, is able to capture a larger piece of the sky with each image that it takes. I just turned it off. And speed. If you're going to survey the sky every 3 nights, you have to do it quickly. Like I say, the sky is a big place. And if you're going to take an image of every piece that you can see every 3 nights, the camera has to be fast and the telescope has to move fast as you move around the sky. So speed is also a factor. And then the ability to see faint objects. If you don't see faint objects, nobody's going to be interested. So it has to be able to see faint objects. And altogether, we get a great movie. So here's a comparison of some telescopes. So here we have Hubble. There's the size of its mirror, 2.4 meters in diameter. And there's the size of its imaging capability. 2 little chips there. If we go to Webb, it's a bigger telescope. It works in the infrared rather than the optical, but you can see that its imaging camera captures a little bit bigger piece of the sky. There's a wide field imaging space telescope put up by the Europeans called Euclid, and it actually captures quite a nice chunk of the sky. Its camera is 609 megapixels. So that's bigger than most people's, much bigger than most people's cameras, probably 10 times or more if you have a digital single lens reflex camera. So as a comparison, here's Rubin. It's got a very unique style here for the mirror, which I'll talk about a little bit. And then here's the field of view on the sky. So compared to Hubble, Hubble is like looking in exquisite detail at a little piece of the sky, whereas Rubin, maybe not as much detail as Hubble because it's on the ground, but it can capture an image of much, much bigger chunk of the sky at once. So Rubin's mirror is like that because it's actually this primary mirror, like the one we have in our lobby, that's a reflective surface. But the center part is actually another mirror. They've polished the mirror, figured the mirror, so we have a mirror within a mirror. So that's why the light collecting part is that kind of donut shape. So here we have a little movie going on while I talk about this. So Rubin will make lots and lots of discoveries. So most of the telescopes today just stare at the sky, take an exposure of minutes, maybe 30 minutes max. But Rubin will be taking 30-second exposures, taking 2 or 3 of those at any one location, moving, taking two more 30-second exposures. And that's the way it will cover the complete sky. But by taking multiple images at each location, you can tell when something moves. And you come back here 3 days later, oh, this is moved. We can see that it's moved. So that's why it will discover things like asteroids that move through the sky. Another discovery will be pulsating stars, which change in brightness. So when you come back and visit the same piece of sky over and over, you'll see the stars that are varying in brightness. And these are not only pulsating stars, but things like supernova, which the star becomes incredibly much brighter as it explodes. And we'll suddenly appear up from nowhere, basically. So things that vary in brightness or move will be discovered by Rubin that haven't been able to be seen by other telescopes in any great number. Once in a while, we make a little discovery. People have done little searches for asteroids and such, but it's Rubin is really going to just really expand the number of moving objects, pulsating stars, supernova explosions, hidden stars that maybe are changing brightness that we don't even know about, and completely new things that we don't even know what they are. And it will do this over 10 years. So not only does it take 30-second exposures and then move on, you can go back and you can add all those 30-second images together, and that lets you go and see the fainter objects. Because a 30-second exposure, even with a big telescope, you're not going to go see very faint stars or galaxies. But if you add all the data together, then you can. So this is the telescope moving fast. It doesn't move that fast, but I want to give an image that gave you the sense of speed. So, as I said, Rubin will scan the sky every 3 nights for 10 years. Some of those nights are going to be cloudy, of course. It's a wide field survey, and it's got 6 filters, so the 6 different passbands, colors that we look through. So that lets you look at different parts of the stellar or galaxy spectrum, and then we get this great time-lapse view of the universe. So some of the science it will do, I mean, this is very broad. Dark matter and dark energy. So dark matter is what holds all the galaxies together, and you know it's this matter that we can't see, baryonic matter. Up until the late 90s, we thought that the universe, as it expands, would start slowing down because all the gravity from all the galaxies in the universe would slowly stop the expansion. And as we look back in time, we would see that expansion slowing down. Turns out it's actually speeding up. So scientists have invoked something called dark energy, this force in the universe that actually is speeding up the expansion. They have no idea what it is. So between dark matter, dark energy, that's 95% of the universe that we haven't got a clue what it is. So it gives us job security as astronomers because we have lots to look for. So it will also look at Milky Way structure and formation. So again, by observing all these stars in our Milky Way, it'll get a really good census of all types of stars in the Milky Way and help us understand how it formed and how it's evolved since its formation. Solar system, again, we have asteroids, comets, we have these other objects outside of Neptune called Kuiper Belt objects. Pluto was the first one discovered of that class. We now know about some number of them, thousands. But this will give us a census of many more, 10 times what we know now, probably 10 times. And then we also, the changing sky. That is how things vary on a scale of minutes to hours to years. We can discover things that change brightness or move in the sky. So this is the dark side of the universe. Anybody that is a 1960s or early 70s actually rock fan of Pink Floyd's Dark Side of the Moon. ChatGPT created that image for me, by the way. Dark side of the universe. So the changing sky. So as it surveys the sky each night, it will detect up to 10 million changes from what is normal, right? So it's going to build up a catalog of objects in the sky, and then each image it will compare the brightness, location of what it sees to what's in this master catalog, and it will flag those things that have moved or have changed. Excuse me. It will send out alerts worldwide to astronomers that something's changed here. This object at this location is 20% brighter, it's 50% brighter, this object has moved, this object has done this. And so astronomers will be able to get those alerts and filter them and look for objects that they're interested in. And that will allow astronomers to use other telescopes to quickly do follow-up observations of those objects that are varying and try and determine more detail what is happening. So some of the technology. Again, I mean, most of science advances as technology changes. So for example, the original mirror, the mirror in our telescope here, was the first large mirror to have a hole in the center so the light could get reflected back down through the center to the spectrograph. That was an advance in technology that made this telescope very powerful. So 3 parts of the technology is the camera, 3,200 excuse me, megapixels, 6 different filters. We have the telescope, this 3 mirror design. So we have that annulus on the outside, that donut that reflects the light to a secondary mirror. And then that center part of the primary mirror has a different shape and then further reflects the mirror to a focus. And it moves very fast from one position to another. Telescope produces huge amounts of data. So you have to do something with that data. You have to manage the data. And so we have 20 terabytes of night transferred to US, Canada, France, UK, and there may be others added on. So that data has to get managed, sent around the world, organized, cataloged, you know, just you have a huge amount. How many people can't find files in their computers, right? I mean, imagine 20 terabytes per night of data that you need to organize. So the camera produces images that are 3,200 megapixels. My digital camera has something like 50 megapixels. You need 400 ultra high definition TVs put together if you're going to look at it in full scale resolution. Its field of view is 45 times that of the full moon. So if you think of the full moon on the sky, 45 times that, it's still a small chunk of the sky. So even though the camera has a very large field of view, it is still only in any one image looking at a small piece of the sky. And then we have 6 filters, and there we have the filters. And if you look closely, there's a person behind here. So you can see the size of those filters. So this is 2-in-1 primary tertiary mirror, very unique. First time that's been done. Telescope weighs 300 tons, the moving parts. It has to move extremely quickly from one position to another. And it has to do that in a way when it gets there, it's stable and it's not jiggling after it moves. So it's a really, really amazing mechanical capability. And then we have high reflectivity, and a large aperture, of course, captures a lot of light. So here we have a little bit about the data from Rubin. 500 petabytes generated over 10 years. Petabytes. So that's 1,000. A petabyte is 1,000 gigabytes, and it's generating 500 petabytes each over its 10-year lifetime. And over the lifetime of the telescope, there will be trillions of measurements made. Yes.
So there is no magnifying.
Yes, it's you know, every telescope magnifies. Oh no, we don't. Astronomers don't deal with like that. It's when you take an image with a telescope. So when you take a picture with your digital camera, yeah, you have a zoom lens or a telephoto. There's a magnification, right? So we don't talk about that in astronomy. What we talk about is what fraction of the sky goes into each pixel. So that's determined by something called the focal length of the telescope. So yeah, we don't talk about magnification, but so I'm trying to think of how to explain that. But no magnification is used in our terminology, but it does capture the full sky in resolution where stars don't overlap each other, so that we see things. So if you have a very poor quality camera, things will overlap. You won't be able to distinguish them. Telescopes are designed so that you can detect small differences, you know, 2 objects close together. So just show you a little movie now. This is a time lapse of the construction. That starts with a big explosion. Yes, it has to be flat, so they need to blast it. So by the way, this hill, that wasn't like this when it was before the telescope was here. It wasn't flat. I don't know if they use dynamite, but we have pictures of them doing stuff by hand and with steam-powered engine machines. So, yeah, you have to prepare the site. So here we have construction during the years. This is 2017. That's what year I visited. They do get clouds there in winter. You can see the auxiliary telescope going up there in the background. Another nice drone shot showing the building is kind of finished, but they're just haven't done anything on the dome yet, or inside ready for the telescope. Takes a long time to build a facility this large and complicated. There's the structure of the dome, and you can see the beautiful vista of the the landscape around the telescope. And all the pieces, had to be shipped to Chile and then moved up the hillside, up the mountaintop. Yeah, the logistics were a challenge, of course, designing it. It's any big telescope, whether it's in space or even on the ground, it's really a lot of work and effort to design it properly so it goes together and doesn't, it fits. It works like it's supposed to. We're getting closer. Get to see some movement in the night sky. And COVID hit, so I think we jump ahead a year, yeah. And there we are putting a top ring onto the telescope. Big crane lowering it in. We got some specs on the lens of this camera, I see. So Chile has a lot of observatories further north in Chile. There's telescopes of the European Southern Observatory, and they're just building a 39-meter telescope up in northern Chile. It will be the largest ground-based telescope in existence.
Why is it getting so many telescopes?
Because it's clear sky most of the time. It's just foothills of the Andes. The air coming in from the Pacific doesn't hit anything, so there's no turbulence in the air. Combine that with lots of clear weather, and you got a great site for astronomy.
300 plus days.
Yeah, yeah. In fact, the region of La Serena, the fourth region in Chile, like a province, it's called the Stellar region. They're really proud of their astronomy. So it's good. Okay, so that's that. Oops, I'm going backwards all of a sudden. Oh, go back. Okay, now this one, if I can start it, this is putting the, no, I don't want to do that. Somewhere down here, it's supposed to be the movie of, there it is. This is putting the camera into the telescope. And how many people have a digital camera where you change the lenses? Okay, and how afraid you are of taking the lens out and making sure no dust gets in and everything. Well, look at the size of this camera. And they have to lift it up and put it into the telescope. So you can see the size of it compared to the people. And there it is, getting wheeled in. Now, all this was planned out, of course. They know exactly how to do it. And it's like this thing, it's a cartridge that fits into the end of the telescope. There you can see the round circle. That's the ring around the end of the telescope tube. And here we see the camera getting put in. Yeah, it's quite amazing, really. It's such a huge camera. It's cooled, of course. These kind of instruments have to be cooled to reduce the noise level. I think it's cool. That's a good question. I'm not sure about that actually, but it probably is cooled. So again, 3,200 megapixels, 64 times the size of the moon. So there it is, putting the camera into place. Oh. Now this one, this one moving. I'll stop this one because it goes on a bit too long, I think. This is just showing the telescope moving. Beautiful little compact telescope. Look how, if you ever have been to the tour of our telescope, it's a very long tube because they couldn't grind a very fast surface into the mirror. And so it's very long focal length, big tube. Look how squat this is. It's an amazingly compact little telescope. And you can see the telescope rotating in azimuth. So it's an altitude azimuth telescope mount. Rotates around the azimuth. Telescope dome turns the other way. And if you've ever, when you go to a telescope like this, you're standing there, the dome's moving one way, the telescope's rotating the other way, it's tilting. You're totally disoriented. Everything's moving in different directions. Yeah, so it's got to do this 300 tons smoothly. So yeah, it's really quite amazing. No, it will not. But it has to move from one location to another very quickly and then be steady right away. Because you have to wait for it to settle down. You're losing time, right? I don't know, but it hardly ever rains there. And if it's at all likely to rain, they close the dome. That's what the dome is there for, protect it from the elements. When I lived in La Serena, each year there were more days where I felt earthquakes than there were days of rain. It doesn't get much rain, but they do get earthquakes. Sorry about this, but the
Clearly mountains are being formed.
no, it's actually subduction. Yeah. So here we have the building. So here's the telescope. So the idea is it's isolated, so no heat from any of the rest of this gets into the telescope and disturbs the air, heats up the air, which makes the images a little blurry. Here we have the facility to recoat the mirror, because every 2 or 3 years it's going to have to get recoated to maintain its reflectivity. And then this is computer room is here, I believe, and then we have other office rooms and things like that, computers and everything go below here. But you notice how all this is totally isolated from the telescope. Very important. Something we've learned over the years, because our telescope wasn't like that. Okay, here we go. Prompts. So a dynamic universe. Like I say, each image, it will very quickly compare it to what was supposed to be there and how bright things were. So these prompt products, as they're called, will be the alerts that something's changed in the sky. Something's gone bump in the night. And all this stuff will get distributed globally. So you don't have to be a part of the project to get access to this type of data. So anybody can follow these alerts, and even with your little backyard telescope, you could go out and look for something that's gone supernova. I mean, anybody could do it. Up 10 million alerts per night. There's lots of data. The guy's getting swamped with data. So here's the first data finally. So this is a region of the sky. So these images, a little bit of a disclaimer. So these were not taken actually with the Rubin telescope per se. I think, I won't say, anyway, maybe they were. But they were taken such that they show what the data will look like after 5 years. So as I mentioned, each exposure is 30 seconds. Every 3 nights they cover the sky, they come back and they do it again and again. And so by adding all those images together, they see fainter and fainter and fainter objects. So the images they showed 2 weeks ago are what the data would look like after 5 years. That is after half of the planned survey. And you can see the multitude of stars here in our Milky Way. So we have the Trifid Nebula up there on the right there. Beautiful little object to look at through a telescope. With your eye, you only see the very center part. We have all these other objects here. It's labeled them all for any amateur astronomers in here. Now, some of you might know these names, maybe not. Lagoon Nebula. Some beautiful images, these pictures of these objects. But this wide field, nobody's ever put together an image this big of this part of the sky before, to that depth. And then we have extragalactic. So now we're looking out of our Milky Way galaxy, looking up, and here we have, excuse me, what the data will look like again after 5 years. And we have a bunch of galaxies and stars. And this can't display everything because we don't have 400 high definition TVs equivalent here. But if you can zoom in and zoom in, you would see more and more objects. But this is a nice swath of the sky showing elliptical galaxies. That's these kind of yellowy, whitish ones. We have some really red objects. The little blue ones are spiral galaxies. And of course, there's some stars in there as well. Up there is a nice cluster of galaxies. All those points of light you see are fuzzy things up there. All those are galaxies. There's another picture of the telescope. These were actually taken supposedly during the observations, but here we have a beautiful view of the telescope and the valleys below. There's the moon. That very bright object on the right is the moon. And here we have a cutout of some of the objects we're seeing in there. Number 4 is this NGC 6544. Some beautiful objects on their own, but they're all embedded in this much, much larger image. And this is just one piece of the sky that's 64 times the size of the moon, but it's still a small part of the entire sky. So here we have that extragalactic view showing some of the galaxies that have names and numbers, and we have a couple of stars. But again, all these are beautiful objects on their own, but we see them on this huge scale image. They're tiny. They're a small fraction of the complete image. I'm not going to talk about that. Another nice image, the moon, time exposure showing the moon. And you can see it's bright, but that's from moonlight. It's not the sun. It's moonlight. Star trails, the Milky Way, and here, southern sky, it's probably the Large Magellanic Cloud. So that's a nearby galaxy, a dwarf galaxy orbiting the Milky Way, only visible from the southern hemisphere. They were seen by Magellan when he sailed around the world, and he thought it was a cloud. That's why they call it the Magellanic Clouds, although they're trying to change that name to something non-European. This one, no, this is probably just an ordinary camera.
Oh, okay.
This is probably, the field of view is so big, this was just a digital camera on a tripod, taking along several exposures, co-adding them, and seeing the Milky Way. We have several excellent astrophotographers in Victoria that take images like this of the Milky Way and other things. So all you need to do is find a nice dark place. And then we have people looking at the telescope at sunset. Of course, when people at the telescope, when they first get data, it is an incredibly exciting event. And so you see all these people that have worked years on this project. And this is a small fraction of the people, how excited they are. It's like, wow, look at that kind of thing. They're either looking at the data or that guy's soccer team just won. I don't know which. Chileans love their football. And then there she is. You can't believe it. And so Canada's involved. I'll just put that up quickly. So Canadian Astronomy Data Center, located just down the hill here. And then they formed something called CanFAR. But all that together, basically, they probably have some of the Rubin data now stored in the big data centers across down at UVic, basically. And so the CADC CanFAR will be distributing data for the public, that is scientists not associated with the project, and that becomes public after, I believe, a year. But they also serve data to scientists working on the project. And then there will be another project based out of Toronto that will serve to handle alerts and correlate it with data and alerts from other telescopes around the world that Canada is involved with. So altogether, Canada are making significant contributions to the LSST, Large Survey of Space and Time. Now, you too can can look at the data. See if this works. There's something out there called Sky Viewer. There it is. So this is anybody can view it, skyviewer.app. And if I got the data there and I can zoom in, oh yeah, it works. So you can see as I zoom in, we are seeing, well, it takes a while for the data to download, but you can see how many stars and galaxies are in this image, right? Just amazing. So if I zoom out, this is what it looks like. Big piece of the sky. But look at, in the detail. Let's go up this here. This looks cool. Oh. So here's this cluster of galaxies. Look how many galaxies are around. And a cluster of galaxies is like a cluster of stars, but each of those is a galaxy with billions of stars in it. And they're all gravitationally bound together. And then we know of thousands of these in the universe, if not more. There's this amazing objects. This sky view, when you zoom in, really shows you what type of data Rubin will get. I mean, the wide field, yes, it looks cool, but it's when you zoom in like that that you see how amazing it really is. So if I just do that, and then there it is. You can bring up your phone again. You can do this on your phone. So when you're waiting for someone at the cafe and they haven't shown up, bring up Sky Viewer and browse the universe while you're waiting for somebody to show up. Or you're riding the bus, wherever. You can look at the universe. You have the universe in your phone. Pretty amazing. And I'll put a quote up here from Vera Rubin. Don't shoot for the stars. We already know what's there. Shoot for the space in between, because that's where the real mystery lies. And that's very true. Thank you very much. Okay.